So, welcome to the first of our colloquia for this academic year. The University of Manchester at Harwell was founded a few years ago now, but it comes to fruition this academic year. So I hope in what I'll say in a moment to give you some idea of the background to how it is formed and the sort of things that it does, but also to give you an idea going forward of how the research areas that it supports are developing around the Harwell campus and back into Manchester and then out from there. Because some of those particular research areas have areas that are of interest not only across Harwell, but out internationally. And there are equally messages across disciplines which allow us to use some of the concepts that we're developing for looking at the physical sciences, of which this campus is so well able to serve, but also act into the medical sciences and then out into the wider engineering. Particularly because we have a role also out into the workplace, as I'll talk in a moment. The idea of borrowing concepts from physical sciences and transferring them across into medical science is one that I'd like to explore today. Hence the somewhat cryptic title, which I hopefully be able to explain to you in a moment. We have set up on the site a series of fellowships in particular areas. One of those that we have recently launched was in the area of nuclear fusion engineering. And we're very glad to welcome Anika, who's just joined the University of Manchester at Harwell, who's acting as a focus in that area for our units down here. There are also areas that we're about to start in data analytics and big data problems for facilities. And also a final one that I want to make you aware of is in the area of extreme geophysics. And that's why we have introduced with our colloquia the topics around which we're going to build these fellowships in the past. And today I'm going to introduce an area that is of personal interest to me, and that is the extreme sciences of one sort or another. So I gave this rather cryptic title, the Exposome of Structures, borrowing two concepts from one from the medical sciences, but one from the physical sciences and engineering as well. And that cryptic title was to try and illustrate some of the synergies that we can make between the two areas of research that we're adopting. Particularly in the modern world, where we're driven by the big data and the data streams that we produce going forward to try and both regulate and understand the structures that we build. The University of Manchester at Harwell was created to provide a base to allow studies like this to prosper on a national laboratory site. It has the basic function of acting as a portal both for the University of Manchester's researchers, but also of their collaborators to access the national laboratories. But equally, it acts as a conduit back to Manchester for all the facilities here in all the different areas that they work. It has a structure that we've set up over the previous years that consists of a core team that has technical support for all of the experiments one can do across the Harwell facilities, one that will allow easy access to the facilities for potential users, whether they be from the University of Manchester, the wider academic community, or industry and other national labs who might want to access the facilities here. And as I say, around it are a series of fellows appointed by the university to lead groups developing here in particular areas of importance. And that's where we'll come to where we are with the extremes area in a moment. We work across all of the facilities here, and those fellows are supported not only by the Diamond synchrotron over the way here, but also the ISIS neutron source, interactions with the central laser facility, and out into the scientific computing department. So we have tendrils out into all of the activities here, and we try and act as a partner for the Harwell site in order to develop the activities here going forward, where we as a community can really help develop activities here. And amongst all of this, we have a small building centered around the nursery, around the back of I-13, where we have our permanent staff sited here. And I'm particularly excited that that permanent staff is now nearly complete, and around which the fellows are almost all now starting their research themes out, as we've discussed previously. The other role that I took on when I came back into academia was to set up an institute with the Health and Safety Executive, the Thomas Ashton Institute. My co-director in this institute is the Chief Scientific Advisor for the Health and Safety Executive. So this is a government-academic partnership, and it has the aims of forwarding HSE's mission to make Britain work well, but also to cover all of the workplace problems around the health of the people who work within there, the plant that they operate within or that they use to do their jobs, but also the processes that they put together to make the business work and to ensure the safety of all the people who work within that workplace. And all of this leads to a more resilient workplace and a more resilient country, if you're going to work on those scales, in what you do going forward. So there are twin concerns that I see every day working on this part of my job. One is the health and well-being of staff within the workplace, and trying to improve that towards a better workplace. And secondly, reducing the risk on structures that we're constructing, whether that structure be a microstructure within a material, or whether it be a plan within a building, or whether it be the components of something like the Earth, where we worry about risks from earthquakes and so forth. And so I'm going to borrow here some of the terminology that was created when they started to try and look at the human genome. Because it was realized by a large number of people in the medical profession that whilst finding the structure of the genome gave one the blueprints for life, when one started to look at health some distance down the line, one had to consider several other things as well. The lifetime environment that one was working in, the choices that we make with how we've lived our lives, and all of that will feed back into the DNA coding that programs the way the body responds to these things. So that to look at the health of twins at the age of 50, one's very unlikely to see that even though they have the same genome, they will have the same health at this time. And so a term, the exposome, was coined in order to describe the state as a function of time within that material. And what I'm going to try and do today is extend that into the physical and engineering sciences to see how the drawing and the materials we choose to construct at the start of the life of a structure can be converted into a consideration that we might make of that structure as it's aged through life, or as it's seen some kind of different environment as one's forgotten to put oil into its works. And we know that time makes a big effect on structures. Just look around us at the buildings we see. I spent a long time in Cambridge, and I lived in the town of Ely, if any of you know it. And this was a photograph of a house near where I lived. And it shows the effects of time clearly there. The sides of this wall are bowing outwards. Because really it's behaving like a thin skin of rubber if you leave it there for a few hundred years. Even for a hard, brittle limestone, looking at Salisbury Cathedral here, if you look up these columns, they have a severe bow in them. They're behaving as an elastic strut because for 1,000 years they've held 1,000 tons and they're bending under that load. So in some senses, particularly at the geophysics scales, strength is a delusion. Strength is a function of where we are and what we're doing to something at the time we look at it. And in order to understand how we might design around these physical processes in order to engineer something for a lifetime, one's going to have to understand the failure and the failure state in the extremes to which that material is going to be, or structure is going to be placed. And that might be conditions at the center of the Earth, or it might be conditions in a building on the Earth, or it might be inside a piece of machinery that we try and work with on the Earth's surface. But either way round, we have to look at things in the same sorts of way when one comes to trying to work out the risk of using these things going forward and the limits which they will see. So what do I mean by extreme states? I have to admit, I've always been someone who gets rather bored with the behavior of materials before they've yielded. Tapping these things and not seeing them fall apart doesn't do a lot for me. However, there are other problems on different scales where deformation and failure are very important. As I say, conditions at the center of the Earth, around 330 gigapascals, are beyond the point where one's got the inner electron clouds interacting with one another, where one has essentially a different state of matter to the one controlled by the valence electron and the Earth around us. Equally, if we look at all our planets, we can see that they are battered and molded by the fact that there's been lots of impacts on their surface over the years. And if one goes to a large enough scale, we also observe that most of these things are spherical. Again, an idea that at scale, strength has little meaning. Of course, there are some events around that which we need to look for. There are periodic extinctions, for instance. The one that killed the dinosaurs 80 million years ago was down, pretty much agreed now to be down to an impact event caused by an asteroid impacting the Earth. And there is no doubt that that will happen again. The question is when. There's also the engineering uses we can put these extreme states through, both in the medical world, when one can use means of getting rid of kidney stones by this method, but also designing for the extremes of space, where we try and put structures at the limits of their material and structural behavior for extreme lifetimes. And then finally, out into the universe, there are the problems of cosmology, where scales are even bigger and problems are even more violent. But it's important to see that even though there have been lots of impacts, both on the moon and here on Minos, we can get information about the states of the material in between. We can look at the effects of impact on Earth. This is Meteor Crater, Arizona. Only about 50,000 years ago when this one hit. But nevertheless, one can recover materials from under here and see the effects of the extremes that have caused these types of failures on these scales. And the scales really are very large within the universe that we're looking at. Just on Earth alone, there are about 200 impact craters now identified. Of course, it's difficult to see them with the movement and weather that's on the Earth's surface and the movements of the mantle and the plates and so forth. The Vrida Fork crater in here, though, more like 2 billion years old, is 300 kilometers across. And so understanding these states is going to be important in order to predict what will happen, because, as I say, we are in a galactic orbit here in the outer spiral arm of a galaxy. We have an eccentric path around there, and so every 100 million years or so, we pass back through the galactic plane. Gravity, therefore, goes up in the environment around us. Also, the number density of fragments created in the formation of our solar system goes up, and the chances of another extinction go up with them. Bear in mind that periodicity is about 100 million years, and that the impact that killed the dinosaurs was 80 million years or so ago. So with an error bar on these things, maybe we need to stop being scared. However, there's been a lot of work done across the national laboratories to look at the effects of high pressure on various minerals. Transitions have been known for many years, and it's possible using the diffraction facilities on things like synchrotrons or on instruments on ISIS with scattering to look at structures and in different phases of materials. But less has been done looking at the defects that exist within them. We've done some work on chondrites. The majority of meteorites are in fact chondrites, and they're formed at the early stages of the formation of the protoplanet. So they come from a point very far back in the formation of the solar system. And those materials are composites and contain with them a lot of defective planes. Those defects are very important because these materials can trap certain chemical materials, and there is evidence that some of the chemicals for the origin of life have been trapped within these sorts of materials. So being able to non-invasively look at these using the facilities here gives us a snapshot potentially on how life itself may be formed. Equally, the geophysics of defects within the planet is another area that's of increasing importance that we can look at clearly now within all the facilities here. This is Mount St. Helens, which managed to lose about 2/3 of its height and 1/4 of its mass in 1980. This gentleman saw that violent event happen, and clearly he was stunned by this. Oops, wrong direction. Because here he is fallen over. This is actually the vaporization of a lake, and the shock wave that went out from there has caused the cloud above it to condense. So understanding all of these violent efforts, the effects both on the Earth itself and on the materials that are contained within the Earth are something that we are focusing on looking at within the new fellowship that's being created. And so if we do this, we'll be looking at a whole series of behaviors in extremes, from the atomic scale all the way through to the cosmological one. And between those, there are whole different responses in terms of the time with which one leaves the material within these states, and also the scale on which they're constructed. And it's this phase space that I hope to show you a potential way that we think we can probe both materials and structures going forward to understand their genome in the future. The extreme states of matter in the universe go from ambient conditions down here all the way up to megabars and beyond when one's into the sort of plasma physics that's done on CLF. And across that space, at different scales, one records different strengths of materials according to the size of the element that one looks at those scales. Each of those scales then corresponds with a particular operational time span. And that defines a defect scale for each of these at which we can look. And if one looks at this, one can see that there are boundaries as one looks at either the time or spatial scale, across which the forces that act within matter to cause it to bind change. And it's those boundaries that determine the way we treat and predict how structures will go forth in the future. Because all of the analysis and experiment we do assumes that with a small number of experiments we can approximate to a regime of behavior. And yet we can see here that around what I'm going to call the mesoscale, these terms for scale sizes are themselves ones that are used differently by different people. So perhaps I'll show you my version of these scales now. The microscale down here, or the atomic scale where atoms are, is clearly determined by the electronic forces that interact to bind atoms together. As one goes out to the engineering scale, one has to joint things together with a weld or a bolt if one wants them to start sitting together. So there is a different force that acts between these materials, and it crosses around the mesoscale. That mesoscale boundary is key to the understanding of how we observe behavior at the scale at which we live, which I'm going to call the macroscale. Because it's that mesoscale that has the critical defects that will determine response at the scale that we want to design for. And so determining where the defects are, determining the regimes in which those defects operate, gives one a framework on which one can start to build a way of designing structures involving these materials. But we need to work out where these boundaries in states are. They're not just in terms of the scale, they're in terms of the magnitude of the forces that we apply. Those may be mechanical, pressure, temperature, compression, tension, or they may be electromagnetic. And it's important to understand the effects that that'll have on the structures that we put within these environments going forward. And so we need to create some means of applying these forces. There are ways of creating extreme states. This isn't one we have in the UK. This is the Z-pinch machine at the Sandia National Laboratories in the US. However, we have got CLF here, which can apply immense pressures at very high speeds, but for extremely short times, in order to tap into what materials are doing within those limits. The problems that we have is if we want to apply these loads, whilst we can get a long way in amplitude, we can't do so well in keeping the load on for any particular length of time. And so one needs to be able to extrapolate from what one can learn in the small times at which one can have a look what's going on to things that are happening over the longer timescales that we care about when we construct our exposome. There are lots of techniques that allow us to look at material microstructure. And it's that material microstructure which is going to clearly determine how something responds. One needs to look within a component we're interested in at the scale below, for sake of argument, 1,000 times smaller length scale than the one at which we're looking, to see the critical defects that will determine the failure at the scale above. And it's determining where those defects are that is really the key thing that I feel that the national laboratories can bring to the science infrastructures we are trying to consider for this area around the world. Everything is defective. The nucleus is defective. They're called isotopes. But as one starts moving out, one gets point defects at the unit cell perspective, what I'm going to call the microscale. The mesoscale, this crossover boundary that we've talked about, has multiple phases, it has volume defects like pores, and it has grain boundaries. And then finally out in engineering at the macroscale, one has a whole series of different types of joints to consider and how they respond. But if one can map across these defect scales, interrogate the microstructures at the scale beneath the one which we can consider, and then enumerate what those defects are and work out which ones of them are critical to the failure that we're going to apply in our environment, we have a way of constructing a path through where we are. A lot of the states we consider we call equilibrium. Nothing is really in equilibrium, unfortunately, because at some scale or other is a defect that's doing something. Whether it's critical over the timescales we're observing it is the question we need to ask, I believe. Talking about a metastable state is perhaps more realistic, and if one's going to do that, one needs to start looking at what mechanisms are going to operate while we're within that state. We can easily find out what threshold it takes to start something off, the bang of a gun if it's for a runner, and we can take a time to see how long it is before that runner gets to the end of their 100 meters. We therefore have both a threshold and a speed for which this mechanism can operate. And whilst mechanisms are operating, states can change within materials. If we halve that particular length over which the running race is, we'll pretty much get the same velocity out of our measurement. But if we make the length of the running track, say, a meter, the runner hasn't got out of the blocks yet or even stood up, since the dominant mechanism for that part of the race is different from the one that dominates for the rest of it. And so the scale on which we do something determines the mechanisms that we're going to look at with our experiments. Similarly, if we're interested in a road surface, the defects that exist there will affect the small scale for some kind of a bug trying to get down this road very much more than it will for an elephant doing the same course. And that means we're going to have to consider the mechanisms and their thresholds that we can start to excite with a particular loading impulse, but also the times they take. Even like we saw for the old house, if it's creep within the structure, within a wall over thousands of years. There's a lot of talk as well about, for rapid loading, a shock or a discontinuous pulse being applied. That shock or discontinuous pulse, and I was a division leader of the shock physics group within the American Physical Society, shocks don't really exist, because if you look at them at the scale beneath, they are just a series of mechanisms operating one after the other. And so whatever scale we're at, from creep at the longest scale down to laser shock at the shortest, we're looking at a scale, at a different microstructure that responds at different speeds with different mechanisms. And we average them together. And I use the example of friction here. A simple law at one scale hides a whole series of microscopic effects going on at a scale beneath. So how do we construct our science at all these scales? We have a suite of Russian dolls of mechanisms and an equal suite of experiments that we can do to give us analysis of what the dominant behavior is within a particular environment. And there are well-developed series of analytical and theoretical tools that allow us to describe these things. But none of them as yet can predict across the scales by just assuming a stepwise progression from one scale or one time scale to the next. One needs a different approach because one crosses these boundaries. And that's where I'm going to try and get to. Okay, now for an example. I'm going to choose a material that responds not only mechanically, but chemically to an individual pulse that hits it. Here is an explosive crystal. And with the excellent facilities in I-13, we can observe that with ptychography down to length scales of around 50 nanometers. And we can see a crack there propagating through that material at that length scale. So in principle, we can see the defects within our microstructures using the tools we have available. But can we see the critical ones? The beauty of an energetic material is if we excite the critical defect above its threshold, it'll start to react. So I want to show you now not only the failure that can occur within a particular geometry, but also results of that applied to a material that shows us how it responds. This is an example of a series of idealized loading geometries that allow us at one scale to look at failure at the scale beneath. This particular one is for fracture. This particular one is to look at simple shear. And within the limits of the environment that we apply, we can see failure at the scale beneath occurring within those materials. And if one puts in a composite and looks in detail, one can see that a simple crack is, at the scale beneath, in fact, a whole integrated zone full of microscopic failures. The ability to apply that to materials and the ability to field materials across the whole phase space in which we're likely to see them is the key advantage we have and the unique capability that we're developing at this national laboratory. The ability to look at toxic materials, this is beryllium. The ability to look at irradiated materials, this is as received and irradiated carbon. And the ability to judge the effect of failure, in this case mechanical failure on those materials, in real time using the synchrotrons. But get me back to those reactive materials. This is an example of a recent accident. This was the Tianjin incident, which killed 173, injured, I think it was thousands of others. And this is just one of the explosives incidents that's happened around the world, this one in 2015. There have been about one every 5 to 10 years of major incidents in the explosives and fireworks industry. There are $1 trillion of industrial use of energetic materials around the world every year. Most of that is mining, blasting, and the pyrotechnics that we put up on it when we have parties. And it's been known for a long time that these things were very dangerous and that no one really understands the physical mechanisms by which these accidents happen. Here's Alfred Nobel, who created a prize to scrub his personality to get over the fact that whilst we've just celebrated the 200th year since the patent of nitroglycerin, he has killed thousands and thousands of people as a result of his product. So how do we find out why these materials are responding? It's because of the defects they contain. This is a simple way of seeing how these materials respond. These are explosives, heated up uniformly in a bath until reaction starts reasonably enough down the central axis. And at an individual point, we can see the creation of pores within that material as it reacts. So whilst this is a uniform heating, the sort of heating it gets during storage, It's producing gas in these volumes as it starts to react to the highest temperatures. And it's that that gives rise to these events that we can't predict. We can create a spark down the center of one. We can create a very localized, short-lived, high-intensity pulse. In some explosive, that's enough to set this material off completely. In others, it controls a channel down the center of it that allows us to work out how the material's responding to this defect within the explosive. And you can see that it's rubblized the material down the discharge path, but it's also taken some of that material, vaporized it, and of course chemical reactions occurred as well. But the most worrying of these is to look at these critical paths to accident that exists within the materials from a very localized defect point heating up within them. We can create a defect in a bed of explosive, and we can see that effect within the material in a column that we've pressed. You can see here tungsten particles, a hot wire at the end of the bed here, and you can see the slow reaction that starts to occur from that very localized, micron-sized temperature source. But that is the result in this particular case. And that process, as we look as a function of a time, occurs in different steps, starting at one scale, down at the micron scale of the wire, and going out to the macro scale and meters beyond all of that, through orders of magnitude in space, and the final process, detonation, occurring at kilometers a second at the end and happening in microseconds. We're moving from a defect to disaster in a very short period of time. And no one understands how we physically get to that point. And more critically, how we put in mitigation inside fireworks, inside the materials that are used for blasting, in order to save lives at the end of this. From the health and safety perspective, 2 people died in the UK as a result of an accident due to that mechanism last year. So back to our extreme states. We can create these and create the boundaries within the laboratory by a series of different loading frames. That will allow us to put the limits on the environments we can test our materials or our structures within. We can do that at different scales, but on the facilities here, we can look at the scale beneath to see the defects that have caused that failure. And we've set up now facilities across Harwell to allow the University of Manchester at Harwell to provide you with the staff and the technical support to allow these things to happen. We've also got facilities here to look in and out of beam at the response of these materials as they happen. But working with the facilities, we want to move to a point where we're beyond taking one-dimensional information spatially in reciprocal space to look at the atomic scale, or looking spectroscopically at what's going on in the electronic states. We want to do all that together, to do it multidimensionally, and to use that to contextualize what's coming out of our material. So it's a matter of applying all of the techniques we have available on the facilities here, all of the states that we might put it into, extreme mechanical or magnetic or electrical, and getting out of that both sensor data to allow us to understand what the states are, but also spatial information to relate it to where we are. And if we do not do that, we can try and create a genome for our structures by using techniques to stimulate the effects of aging on our materials and structures. Finally, the data we collect needs to be looked at in a different sort of way. Because if we can create a set of data within the boundaries of the environment we're interested in, and we can create the analytical laws that allow us to predict response within that from the critical defects we observe at that scale, we have a means to allow the supercomputing of today to calculate across all of the possible states that we may access within the bounds that we're loading those materials to. And that way, we have a predictive capability that comes from producing, with the deep learning and data analytics that we have available to us, the sort of response we need to design structures for the future. So, in summary, we have set up a capability to look with the particular facilities available at national laboratories. There are across the UK, universities and industries, amazing resources now to look in great detail at microstructures with laboratory scale capabilities, X-ray tomography machines, small spectroscopy machines, etc. And so microstructure is attainable to everybody. But to do true in situ experiments, to look at the mechanisms and how they evolve, is how we need to use this national laboratory around all the subjects we're interested in. We have the range of sources here unique internationally, where one can walk from the neutron source to the laser to the synchrotron with one's experiment. And we aim to provide the means to do that with the sample environments that will allow you to load your materials in any of those places. We developed the techniques to allow us to develop this genome out of the data that we're generating from our experiments. And then we can use the deep learning in the massively parallel machines of today, both to better analyze the data in the petabytes that will soon be coming off these machines in order to look at response, but secondly, to construct the models, as I was telling you, to give us the framework to map response in the areas we're interested in. And that will allow us both to input physically based material models with the defect structures that are real to their subjects within the sort of codes that will allow us to look up the response of the material and look at that structure as it ages on the computer. So hopefully I've given you an idea of where we're aiming with the efforts that Manchester has set up down here. We shall shortly be advertising for the post, the fellowship in the area of extreme earth sciences. And I hope I've shown you how the sorts of experiments that it will do will affect earth science, but also how it will spill over into the physical sciences and engineering as well. In parallel with that, we're looking at the artificial intelligence and the data analytics that comes from the groups that Tony Hay has set up in the scientific computing department. And hopefully soon we'll apply that to the extreme environments in the Harwell Space Cluster, talking to our friends in RAL Space over the road. So I hope that we can put all of this together. We can connect experiment, create an exposome, populate a phase space, and simulate the future, and use that to regulate for a better world of work and a better way going forward for us all. And certainly the health and safety executive, putting my other hat on, would be keen to support us all here in doing that together. All of that has to be bound together by the immense advances that have been made in computing and the way that we connect that both to the simulation but also to the extraction of big data going forward in our experiments. And so, I hope I've shown you how we might be able to create a quantum of behavior at a small scale within a national laboratory, particularly in front of either a light or a particle source on the Harwell site. If we can do that, we will be able to hopefully then develop the tools to allow us to populate this phase space with the response of any of the structures we consider, regardless of their scales. And if we can do all of that, we've got a new path to assurance, potentially, if we can convince the regulators that this would be a route forward for us to take our research going forward. And if we can apply this equally across the medical sciences, the same sorts of models apply to populations of people as well, then one can potentially use a parallel model to help us all age better and live our lives well. And with that, I'd like to thank you very much for your attention. Hope that you'll join us in a moment through on the other side to see the work of the other people within the University of Manchester at Harwell, and finally hear of more of our research and how we can use that along with you to take our collaborations forward. So, thank you very much. I'll be chairman as well. Any questions? Or shall we just go next door? Can I, before I leave, point out that we do have some activities coming up for this academic year from UOMAH. The colloquium, clearly you know about, but we have a workshop that's being organised for active materials. There are participants from other people around the UK in these areas, Imperial, UCL, Bristol, I know of, there may be more. And that's being run in parallel with the Dalton Institute in Manchester. And that will be held then, so if anyone's interested, please get in touch. Putting my other hat on, the whole area of monitoring and understanding structures in extreme environments is of interest across government and across other agencies. And there is a 2-day workshop, Managing Risks from Aging Infrastructure, which will be held in Manchester on the 29th of January, to which you're very welcome to get in contact and register for. And then finally, to follow on from last year's event, we have a date for our Harwell Manchester Roadshow on the 1st and 2nd of April, where the facilities and the university will be coming together in Manchester to discuss areas of interest and challenges and new avenues going forward. So, do please join us. There are drinks and refreshments outside in the atrium, and thank you very much.